Well, Brecken, I can't add Brecken because that's his email address from school, which he doesn't have anymore. But otherwise, I would happily... If you give me his other address, I'd try and add him for sure. All right. Hello and welcome, Gia and Caitlin as well. Today, we are looking at Chapter 6, which are further functions, some of which we'll have seen before. We'll have seen a little bit of this, a little bit of that, and that may be about it. There were like 3 questions in Year 10 on partial fractions. First thing, even and odd functions. They're just definitions, names of functions that have some special properties. An even function has the property that f of negative x is equal to f of x. So whether I put in 2 or negative 2, I get the same answer, or 5 or negative 5. You can see the one that we're most familiar with, f of x equaling x squared, is symmetrical about the y-axis. If it's symmetrical about the y-axis, it's going to be an even function. It's just a definition of what an even function is. So all you really need to remember is that an even function, whether I sub in positive or negative x, the answer is the same. In fact, any even-powered polynomial where it's just y equals x to the power of n, if that power is even, hence the name even function, it's going to be symmetrical about the origin, isn't it? What does x to the power of 4 look like? Looks like a parabola that's a bit wider and fatter. X to the power of 8, even more vertical and even more flat. They look the same. Until I put a scale on it, you can't tell the difference. They all look the same. So even powers of x always have that shape. Hence, they decided to call these even functions. All right. Odd functions. If there are even functions, there are also odd functions. A function is odd if f of negative x is equal to the negative of f of x. What does that imply? An odd function has rotational symmetry about the origin. So rather than being reflective symmetry, symmetrical about the y-axis, an odd function, I can rotate it 180 degrees about the origin and it will have the same shape. That's all there is to them. Definitions of functions. Determine whether each function is even, odd, or neither. We're going to have a look at those examples right now. What does the graph... Yeah. They're just not special. Yeah, but there are probably names for all sorts of different other specific functions, but no. Mostly, odd and even is not something we do a lot with, but it comes from the fact that polynomials, like every odd-powered polynomial, has that same basic shape. Every even-powered polynomial has that same basic shape, if we're just talking about x to the power of n.
So what's the point?
It's useful in certain situations. That's when you want symmetry, either reflective or rotational. I guess that's why it's... Symmetry is important in a lot of things, right? So having a symmetric property can be useful, so sometimes trying to manufacture an even or an odd function might be worthwhile.
Is this something we use, like, have all in tests?
It's not something... Other than them just asking about it, no, not really. But you can save... Like, if something's an even function, then you can save some time because you can go, oh, the integral between 0 and 7 is the same as between negative 7 and 0. So if I've already got the answer for the right-hand side, I can just double it to get the total. So there are some properties like that. Or I can use the rotational symmetry to say, oh, this area is the negative of the other area, but they're the same. So apart from saving time, there's not a lot that we do with them at school level. There are probably things that someone somewhere does with them in a maths department because it's interesting for them. Or if it's in a manufacturing, industrial context, maybe making something with symmetry is really good for reflective surfaces inside a cable to make the signal travel further. I don't know. There would be reasons why they would be useful. Did we draw 1 over x while we were thinking about that? Is everyone happy that that looks pretty much like 1? Did I make it 1 over x? Did you agree with me? If I want to be really clear, I could put in the 1, 1, and the negative 1, negative 1. What do we think? Is that an odd function, an even function, or neither? Are you calling out to me there, Gia? Or Caitlin. I can't hear it. I was hoping you guys were calling out the answer for me. That would have been fun for me. Do we think that has... Does it have reflective symmetry in the y-axis? No. If I fold it over in the y-axis, no. So it's not even. If I rotated it 180 degrees about the origin, would it look the same? I think it would, wouldn't it? It has rotational symmetry. So that would be an odd function. If I rotate it. What's the other way to check? So I can check it by symmetry. What was the algebraic way? F of negative x is equal to the negative of f of x. Well, let's have a look at f of negative x. F of negative x equals 1 over negative x. Could I rewrite that as negative 1 over x?
Yes.
I could, which is negative f of x. So it meets the algebraic condition as well. We can do it with algebra, or we can do it looking at the graph. Ideally, we can do both. Oh, x to the power of 4 plus x to the power of 2. It's going to look a little bit weird, isn't it? But they're two symmetrical functions. If I add symmetrical functions, does it make sense that the points would still be symmetrical? I think it does. So just thinking about the graphs, even though I don't know what the exact picture looks like, I'm thinking that's going to be an even function. How would I check it? G of negative x equals negative x to the power of 4 plus negative x squared. Oh, that's x to the power of 4 plus x squared. Oh, that's g of x. Yeah, g of negative x equals g of x. It's definitely true that it's an even function. H of x equals x squared minus 2x plus 3. Oh, is that the same as x take 3, x plus 1? I think it is. If I had a look at that on a graph, it's got an intercept at negative 1 and at 3. It's a parabola. It's an even-powered function. But is it going to be nice and symmetrical about my y-axis? No, it's not, is it? And we can check that. H of negative x is going to be negative x squared minus 2 times negative x plus 3. And that's where the problem comes up, isn't it? I get my x squared, but now I've got plus 2x plus 3. You can clearly see that that's not the same. Why is this annoying thing here? Can I get rid of that? No, I guess not. I could have checked h. It didn't equal h of x, nor did it equal negative h of x. So it wasn't, it didn't equal h of x. It's not even. Nor did it equal negative h of x. So it wasn't odd. So that's why I could say it was neither. And from the graph, it's obvious that it doesn't have reflective symmetry, and it doesn't have rotational symmetry. So we're done. That's it. Prove that the sum of two odd functions is also an odd function. Left. Let h of x equal f of x plus g of x, where f of x, g of x are odd functions. Are you happy that now I have a function which is the sum of two odd functions? Yeah. Okay. What would h of negative x be? Each of those is an odd function, so I can say it's negative f of x plus negative g of x. I could factorize out the -1, and I would have f of x plus g of x. Oh, that's just negative h of x. So therefore, it's an odd function. Yeah.
You have to include this step negative bracket f of x plus g of x, or could you go straight to negative h of x?
I would include it, just to make it really clear that it's negative h of x. I've produced h of x in my working, rather than just... It's the same thing, you're not wrong, but I think that line's important in a proof. I think this line here, that's the question was, do I need to include that line or not, or can I go from this one down to there? I would argue in this one you want to make sure if h of x is here, f of x plus g of x, I want to make sure I've got negative h of x inside those brackets. I wanted to get the f of x plus g of x visible so it was easy to see the proof. Odd and even functions, there are a few questions on them. They're not particularly hard. Any questions from home? Oh, they're already in the pool. Can you hear them? Oh, was that a well?
No.
Oh, it was a no. I was getting excited that I was going to have a question. All right. Part B for this chapter, graphs of f of x squared. We can probably in our heads start to picture what's going to happen here. Definitely everything below the x-axis, where I've got a negative y value, is going to be reflected above. And then every point, every y value is being squared. So I'm going to stretch it vertically, but not in a linear fashion where everything's being stretched by the same amount, in a quadratic fashion where the further away you are, you end up that much further again. You multiply by that distance. That's all that's really going to happen. I made a little diagram of all of these little things, which if you want to, you can explore. I don't think we'll explore it now, but basically everything in this little investigation on the left, I've got them color-coded so that the graph of... I'll show you quickly, maybe. Oh, is it going to work? Maybe not. Maybe Desmos will crash. But you can go to the link and at least join to it that way as well. All it does is show you that our intuition was pretty accurate. Okay, it's not going to let me do it now. What are the important bits and which bits are surprising? I think none of it. Let's have a check. A point with a y-coordinate of 0 or 1 is going to be invariant. That makes sense because 0 squared still equals 0 and 1 squared still equals 1. Is that fair enough? Yeah. The graph of f of x squared touches the x-axis at its intercepts. Well, that's exactly the same as saying the points at 0 are invariant. So, yeah, that makes sense. The graph of f of x squared lies above or on the x-axis for all values of x. Tick, we already knew that because we were reflecting it in the x-axis anyway. All the bits below the axis came to the top. If there was a vertical asymptote, then there's still a vertical asymptote when I square it, because I've got an undefined value. Squaring an undefined value is still undefined. Yep, that makes sense. One which I didn't mention but makes sense when you think about it. If x is a value between 0 and 1, and I square it, what happens when you square a fraction that's between 0 and 1? It gets smaller. Half times a half is a quarter. 10th times a 10th is 1/100th. So it's actually getting that much closer to the x-axis. And if the absolute value is greater than 1, then it's getting that much further again. And I didn't want to open that. I'll see if it'll open it from the link. Here we go. If I turn off all of the extra ones... Oh, I didn't keep my color coding. That's really annoying. Well, there I have a line. If I just had a straight line, x plus 1 squared, what are we expecting? This point here, at negative 1, 0, that's not going to change, is it? This point here is also going to stay the same, isn't it? When x is 1, 1 squared is 1. These bits between it, instead of being a straight line, it's going to curve down a bit. Why is it going to curve down? Because those values get closer to the axis. all this straight line to the right, what happens when I square it? Starts curving up, doesn't it? This little bit that was negative, it's going to go here and curve up as well. So if we look at f of x squared, imagine that we've got a parabola. That makes sense, doesn't it? Because isn't that just the graph of x plus 1 all squared? It's a parabola that's been shifted 1 unit to the left. So that makes sense.
So if you get x plus 2 all squared would be shifted to the left by 4?
No, because x plus 2 in brackets all squared is still just shifted to the left 2. X squared minus 4. The points that aren't going to move, let's find them. Right here, where x is equal, or where y is equal to 0. So the 2x intercepts. Also, the points where y is equal to 1, which appear to be there and here. So those points are going to be the same. Well, it's going to get a bit curvier. That's really all that's going to happen. Because what's going to happen is my x to the power of 2 function is going to be x to the power of 4. Remember when we drew that on the board, like on the whiteboard before? Instead of being skinny, it was shorter and fatter. Yeah. So when we square it, it got wider, but in between was the interesting thing. This bit of the parabola here got reflected and then squared. I can't see where the top is.
16.
The top's going to be at 16. Why is it going to be at 16? Because I'm going to take negative 4 and square it. And we go up to 16 exactly as expected. Oh, that's nice. So on occasions, I'll leave you to explore the rest. We don't need any more time on that. But on occasions, in exams, they'll ask you, they'll give you a diagram and they'll say, sketch f of x all squared. Doesn't move when the y values are 0 or 1, and then it stretches. Usually you would only need to plot those extreme points. So like that turning point, which was at negative 4, we move it up to 16. That's all we've got to do. Nice questions. Nothing too terrible about them. If we were going to draw that one, and we were going to sketch it really quickly, we were going to square that. Do you want to do it yourselves, or do you want me just to go through it with you? Hey? Do it yourself first. Picture it yourself. See what it looked like. It's a sketch. It's not a scale drawing, but there are 3 points that should be labelled. I want to see those 3 points labelled. I like that. Yeah, I'm with you. It's just me. I'm sorry.
So maybe if you gave it to your Pepsi, I would feel...
Look how little there is left. Imagine how many people will die before the end of the day if I didn't have this just to keep my sanity.
Still,
Yeah.
end soon, so you should give me a bit.
I could murder a lot of people in the time remaining. We've got 20 minutes. I'm saying this all on camera here. This is good. Yeah, it's on record. Just in case you're wondering. Don't steal my Pepsi. No, but I'd take the bribe. This is the way bribes work. I will accept all bribes. It will in no way influence any mark I give you, but I'll take the bribe. I'm not too proud to beg. The halo effect. Yeah. I'm going for the I don't have a lot, I'll take it, sure. If you can afford to spare it, I'm not too proud for charity.
I'm saying that currently Coke is the only thing that's on for cheap at the IGA, so we'll accept that.
Oh, it is cheap at the IGA at the moment, isn't it? That's pretty good. Where's our .43 go to? I don't like Coke Zero though. You guys are great. And then it's increasing really steeply because now instead of resembling a quadratic, it's resembling a quartic, so it's going really steeply. How'd we go at home? Something like that? They are. They're in the pool. They're not there. They're just having a swim, putting their feet up.
We understand.
Oh, good work. Are you sure you're not in the pool?
I can't leave my room, so...
I know, that's so harsh. Oh, you can imagine it though. Oh, nice. Oh well, have a swim for Caitlin too. All right, we're doing well. Part C. Absolute value functions. These are the ones we did a bit of back in the core textbook. Step functions are where you've got like different things. Absolute value are just the ones, everything that's negative becomes positive. So it's like what we just did, except we don't square anything. The shape stays the same. Yeah. So y equals x, they've reflected the bit that used to be in the negative, and they've reflected it and made it in the positive. It's the same thing. If ever you're asked to sketch the absolute value of f of x, it's f of x with all the bits below the axis reflected in the top. But you don't need to rescale it. So it's even easier than the first bit. So sketching them and reflecting them is not a challenge. There is a challenge when we get to f of the absolute value of x. When I'm not taking the absolute value of f of x anymore. I'm not taking the absolute value of the y function. I'm doing f of the absolute value of x. When I'm doing that, think what happens. I've got all the bits where x are positive, or for you guys that direction. I don't know what it's like for you at home. I don't know whether I'm reversed or not. That's going to be the same, isn't it? When all the x's are positive, it stays the same. For all the negative x's, they now correspond to these ones, so I'm going to create an even function. The negative is just going to be a reflection of what was on the positive side. So this is one way you can create even functions from any function. If you have any function f of x, and I go f absolute value of x, I've now created an even function. It's that easy. So, and that's what they're saying here. Discard the graph for x is less than 0. So we get rid of that bit where all the x's were negative, reflect the graph for x is greater than 0 in the y-axis. So we reflect it. So we keep what we started with as well. So we have the original image and the reflection. Rather than reflecting the whole lot, we just keep it there. Anything on the y-axis stays where it is. Draw the graph of 3x times x minus 2. What sort of graph have I got? Parabola. What are my intercepts? 0 and 2. Happy or sad? Happy. Nice. So this is going to be pretty easy to draw. I'm sketching it so I'm not losing too much sleep over it. That's good enough, right? That's my f of x. On the same set of axes, sketch the absolute value of f of x. Let's use a different color. Let's go with, I want something different. Let's go orange. Absolute value of f of x. Anything that was negative becomes positive, but the shape hasn't changed. So this is just a perfect reflection of the other bit. And then these bits are the same. They're on top of each other. Assuming I could draw that reflection perfectly, that is the absolute value of f of x. Anything that was below the axis gets reflected above. Anything that was above stays where it is. Anything on the axis stays where it is. Okay, we need a different color for the absolute value of f of x. Absolute value of f of x, everything that was positive stays where it is. The negative stuff I get rid of, and I make the symmetrical graph on the other side. That is f of the absolute value of x. I kept the bit where x was positive, and I reflected it across the axis.
Let's try it. Which one are we doing?
Oh, that one's not fun enough.
Can we do like a power of 16? Oh!
Exponential function. That's k of x. If I do, first of all, I'll do the absolute value of k of x. Oh, good. It doesn't do it till I do the y equals. So, the absolute value of the whole function, anything that's negative, gets reflected and made positive. So this little bit that's going underneath there is just going to pop up and curve away above. So when I put the y in there, can you see that the bits that were below the axis got reflected above the axis? Okay, that's good. What about if I moved where my absolute value was from outside of k, I'll just get rid of the y again so we can think about it first, to just being the absolute value of x. So this bit all stays the same. Everything where x is positive stays the same. And now that exponential part is going to be repeated over here, because everything on the right-hand side stays and gets reflected onto the left-hand side. So you can see, the bit on the right got reflected on the left, everything else stayed where it was. That's not a quadratic, that's an exponential. It looks similar, doesn't it?
Yeah, but then the turning point's off.
Yeah, but it's not a turning point. It's a... Because that's actually not a nice smooth transition there. The gradient is different as I approach from the left and the right. So the derivative at the actual point there, 0, 0, doesn't exist. Because the gradient's not well defined. When I go from the left and when I go from the right, I've got different gradients. So we don't. That's a point which doesn't have a derivative. But the function still exists at that point. It's still at 0, 0, 0. And I've got the shape. It looks a little bit parabolic, but it's not. Lots of functions which increase quickly, people call exponential when they're not. Exponential equations, x is in the power. X to the power of 6 increases really quickly. Looks the similar sort of shape, but it's not exponential. The reverse is also the same. This was an exponential graph, and on either side it's exponential. It's not a polynomial, it's not a power of 2, power of 4 or anything, but it looks pretty similar. Equations that look similar but aren't the same, they do exist. So, they're the two ways you do it. Nothing else special about them. Sketching f of the absolute value of x, reflect it in the y-axis, only keep the bit that was on the right. Absolute value of f of x, anything below gets flipped up to the top. We sometimes have to solve modulus equations, and we did a little bit of this as well. There are just two ways that we do it. One way to do it is you just let the bit on the left, so 2x plus 3 equals 7, or 2x plus 3 could equal negative 7. Because the absolute value of negative 7 is still 7, isn't it? And then you just solve that, and I've got the two values where it's going to equal 7. Okay, you do the other one. So the easy way, the easiest form of modulus equations, I've got an absolute value equals a constant. Either what's inside the absolute value equals the positive of it or the negative of it. Oh. I didn't read it, did I? The absolute value of something is either 0 or positive. Can the absolute value of something be negative 1? Nope. No solution. Question. Yeah? Yeah. Oh, well, a log function goes up really slowly, doesn't it? Exponential? Yes, yeah. That's like the last one I did. It looked like a parabola, except it was pointy a little bit at the bottom. Exactly right. If I had it on the outside of it. If it was just 2 to the x, like there was nothing below the x-axis, it would just stay as 2 to the power of x. Because 2 to the power of x doesn't go below the x-axis because that's the asymptote. Yeah, good question. When I have these fractional ones, it's really no different. I can still do the same thing. What am I going to do for the first one? 3x plus 2 over 1 minus x equals 4. Or, I said plus 2 and wrote plus 1. 3x plus 2 over 1 minus x could equal negative 4. I can go ahead and solve these now. So these ones are not too bad, right? What are you going to do for the other one on the right-hand side? Yeah. You can just go with x plus 1 equals positive or negative 2x minus 3 and it will work.
Oh yeah, actually. Yeah.
Oh, all right, plus 3. You have 2 minutes to do those two. Well, the two, the one on the left and the one on the right. Oh, you girls at home can sneak a look at the answers. Maybe. Oh, except I haven't got it open. I had them open all day and then I've obviously closed them because I got frustrated with having too many open windows. That's funny. Oh, I don't know that the 8 minutes we're going to have left after you do this problem is going to be enough time to finish. It's going to be disappointing. Yeah, 2/3 or... I left the working out to see if you guys got them right. 2/7 and 6, 2/3 and 4. Boom, killing it. Nice. How'd you go? What'd you get?
I got the normal way right, but when I tried doing it, like I got the 4 and the 2/7.
Yeah.
But I think I did it wrong with the 2/3 part.
Oh, okay. Is it just distributing the negative? Like when you got, I think it is. Like you just got to go negative 2x plus 3, or when you're doing the one on the left, the purple one, you'll have negative 4 plus 4x equals 3x plus 2. That's probably all it is.
Yeah.
So you can... Could you bring that 1 minus x to the other side and then take the plus or minus on the other side? Could you do it that way?
Could I multiply by the absolute value of 1 minus x?
Yeah, and then...
Yeah, it should still work, but it seems like more effort.
Just put it in the...
I mean, you're multiplying by as long as x doesn't equal 1, but it couldn't equal 1 anyway. Yeah, that would work. It goes on to talk about modulus inequalities. Guess what? We still do it the regular way. Where it's less than 3, it could be greater than negative 3 or less than 3. Like what we do with our absolute, when we're doing geometric series, what's the condition for it to have a finite infinite sum? The absolute value of r is less than 1 is the same as r is between negative 1 and 1. If it's a greater than 1, You do it's greater than that number, or it's less than the negative of that number. The only other way you might do things is if we know that it's definitely positive. We can just cheat and square each side, because I'm not squaring a negative. So if I've got an absolute value is greater than or less than another absolute value, it's fine to square each side, because they're both positive to begin with. If I've got an absolute value is greater than or equal to something which is a positive number, I could square each side. So that's what I've highlighted there. If we know each side is positive, we can get away with squaring each side. Otherwise, you just consider the two cases. They're all going to work. We're going to miss out on doing rational functions this week, and we're going to miss out on doing our partial fractions. There's only 2 little bits left to go in that exercise. That's probably enough to keep you going over the weekend anyway. Yeah, of course. We're here. So it's greater than or equal to 5, or it's less than or equal to negative 5. Because when you multiply by a negative, what happens? You have to change the direction of your inequality sign. That's all you have to do. All right, we'll finish that off next lesson.